All right, let's go ahead and start with that problem that says the following. We have a differential equation, dp dt is equal to s times p. Is that an s or a 5? Okay. Times 1 minus p. And we're given that p of 0 equals p naught, which is always the most annoying choice. S is a constant. Find the solution. Okay. Yeah, we actually don't think we've done one quite like this, so this is a good one to do. So solve, right? So yeah, solve it. So if we're solving it, we know it's either first order linear or separable, and it's probably separable. This one looks separable to me. I'm going to bring all my p's to the left. I have 1 over p times 1 minus p dp equal to everything else on the right, s times dt. You could bring the s to the left, but again, if I have the choice, I'm usually putting as much stuff as I can on the side with the independent variable. So I'm going to push all the things to the t side if I can. Let's integrate. Well, to integrate this, we have to use partial fractions. So over here, we're going to say that 1 over p times 1 minus p is equal to a over p plus b over 1 minus p. We multiply both sides by our common denominator, which is p times 1 minus p. So we end up getting 1 on the left equal to a times 1 minus p plus b times p. We pick nice values for p. I'm going to pick p equal to 0 and get 1 equal to a times 1. So a is equal to 1. I'm going to pick p equal to 1 and get 1 equal to a times 0 plus b times 1. We get b equal to 1, which is pretty typical for differential equations problems where you have partial fractions. Is usually the partial fractions decomposition is pretty easy usually to find. Like it's usually very nice. Both things are 1 or 1 and -1 or something like that. So then the left-hand side is going to be the integral of 1 over p plus 1 over 1 minus p. And the right-hand side, let's go ahead and integrate and get s times t plus a constant. Continuing on, we integrate 1 over p. Let's see, how careful do I want to be here? I really don't want to be that careful, but I'm going to be careful. The integral of 1 over p is the natural log of the absolute value of p. And the integral of 1 over 1 minus p is the negative natural log of the absolute value of 1 minus p. Still equal to s times t plus c. The reason we need the minus sign there is because if we differentiate the natural log of 1 minus p, we get 1 over 1 minus p times the derivative of 1 minus p, which is -1. So we need that -1 there to adjust for that. And then let's see, find the solution. Interesting. Okay. I feel like there's more questions we could ask here. So we're trying to solve for p. So typically that means we have to combine the logarithms together as one logarithm. So we're going to write this as the natural log of the absolute value of p over 1 minus p equal to s times t plus c. And then we're going to exponentiate both sides so that the absolute value of p over 1 minus p is equal to e to the st plus c. But we've done this enough times that you should jump straight to saying it's e to the st times e to the c, which is then e to the st times a new constant, which I'm going to call a. I think it's a perfectly legitimate jump to get to right there. And at this point, we could probably drop the opposite values because a will be positive or negative as it needs to be. So we can say, great, p over 1 minus p is equal to a e to the st. When I do this, I usually multiply both sides by 1 minus p, distribute, bring all the p's to one side, factor out, divide. Some other people prefer just to take the reciprocal of both sides, which also works kind of great. Take the reciprocal of both sides, you get 1 minus p over p equal to 1 over a e to the st. And then you get 1 over p minus 1. I don't love that. Really, yeah, I just am not a fan. It's fine. This will work out, right? This left-hand side is just 1 over p minus 1. And then you can add 1 and then take the reciprocal both sides again. I find that pretty annoying. I'm not going to lie. I think it's terrible. But you could do it that way if you wanted to. I'm going to do it the way I like, which is instead say that P equals A e to the st times 1 minus P, distribute, get P equal to A e to the st minus A e to the st times P, bring that over here. P plus P times A e to the st is equal to A e to the st. Factor out of P. And finally, solve for P. Then we have that P at time 0 is equal to P naught. So the question always becomes, where would it have been best to find P? Or sorry, A, not P. Good question. I don't know if I have an answer here. I'd probably just, I guess I'd probably back over here where I had P over 1 minus P equal to A e to the st. That might have actually been the best moment to find A, because if I plug in T equal to 0 and P equal to P naught, I wish they could have given this a real number. I'm going to have P naught over 1 minus P naught equal to A times e to the 0. So that's my A. So I can plug that in over here and say, great, my P is going to equal, now it's going to look kind of gross for a second, P naught over 1 minus P naught times e to the st over 1 plus P naught over 1 minus P naught times e to the st. I would make the pretty typical choice here of multiplying the top and bottom of this by that denominator 1 minus P naught. And rewriting this as P equal to P naught e to the st divided by 1 minus P naught times 1. And then 1 minus P naught times P naught over 1 minus P naught is going to be P naught e to the st. That's probably a more typical way of writing this final answer. Interesting. For me, I'd probably ask a follow-up question like, what's the limit of this as t goes to infinity? Because that's often a question we like to ask. And if t goes to infinity here, the limit's going to be 1. Because this part here and this part here are both kind of doing the same thing. And then this part here becomes inconsequential. You could also more easily calculate that by dividing the top and bottom by e to the st. And then seeing that these two terms are going to go to 0 and these terms are just P naught over P naught. Interesting. I don't know if I like this question. I don't like these questions in general. Well, actually, specifically these partial fraction ones, when you have to solve them, because solving them takes so much algebraic manipulation. It's always this process where you have like the natural log of a quotient, and then you have to write it all out, or e both sides, and then do P over 1 minus P naught, and then do all the algebra to get, it's just kind of tedious sometimes. That said, it's not impossible to do. It just takes determination and careful attention to the algebra that's happening. Any questions about that one? All right. Let's look at the next one that isn't the Euler's method question. They've got some stuff for Euler's method here. So let's look at this d mu dt equal to k mu to the 2/3 minus mu times m. People just use nice constants. Why do we gotta use these Greek letters? Okay, so we have, let's see here. We have d mu dt equal to k times mu to the 2/3 power minus mu times m. Oh, so I'm concerned there's something amiss here. Oh, I'm sorry. So sometimes an m can look like a mu. I apologize. So let's try this again. Apologies. Let's try one more time. So it should be correct me if I'm wrong. dm dt equal to k times m to the 2/3 minus mu times m. Okay. Yeah, it's just like, why do we use u and v for integration by parts? They occasionally just look too similar. So we're given that mu and k are both constants and they're both positive. Great. And we're first asked to assume that k equals 1. And we have the m of 0 equals 1. And then we're asked to find, we're asked to solve. So find m of t. Yeah, all right. Well, this is not bad. Well, is it bad? I don't know. Yeah. Yeah. What do we do here? Let's see. It's not first order linear because I have my m to a non 1 power. That's probably the worst way you could say that. So I guess it's got to be separable. Yeah. Solve? M as a function of t. Okay, okay. We're given that k equals 1. Okay, so we've got dm dt equal to m to the 2/3 minus mu times m. We don't know what mu is yet, or if, yeah, we just know that mu of 0 is equal to 1, but, or sorry, that's m of 0. Do not love the choices of m and mu here, sorry. M of 0, okay, we don't know what mu is at all. That's fine. So, thoughts? I mean, I have a thought, but I don't like it. Yeah, but I think the problem, I think to separate here, we divide both sides by the entirety of this. Like there isn't another choice. So I think we have to write this as 1 over m to the 2/3 minus mu times m dm equal to 1 or just dt. Because to take the integral of the thing with m's and the m's have to be on the same side as dm. Because if I'm putting it over here, like if I have my m's over here, I'd have to be integrating with respect to t. So when we separate variables, it means we're not friends with each other, right? If the m's on one side, the t's on the other side. So all the m's have to come to the left, all the t's have to come to the right. And the only thing we're allowed to do is multiply and divide. I don't see another way around this unless I'm missing something that's obvious. Right, it is k times m to the 2/3 minus mu times m. We're sure about that, so I'll make sure. Okay. Remember, there was that one time we had that really terrible question that really shouldn't have been that terrible because there was a slight error. Let's make sure. All right. Hmm. Yeah. Uh, what do you do here? Okay, maybe that'll work. Let's try this. So I think if we factor out an m to the 2/3 from the bottom, we'll be left with a 1 minus mu times m to the 1/3. Yeah, this will work out. Okay. Tricky. Super tricky. We're going to integrate both sides. On this side here, we're going to do a u sub, and we're going to let u equal the 1 minus mu times m to the 1/3. That's a terrible pen. I should just throw you away. Because what's going to happen now is that we take the derivative, our du dm is going to equal negative mu times 1/3 m to the negative 2/3. Or just leaving this on that side, I'm going to have, okay, don't confuse my u with my mu. They're different. So I'm going to have du, and I'm going to have times a 3 divided by a mu. So I'm going to have a 3 over mu, negative 3 over mu du is equal to m to the negative 2/3, which is 1 over m to the positive 2/3 dm. We're in business because we exactly have a dm divided by m to the 2/3. So we're going to rewrite this left-hand side as the integral of the dm over m to the 2/3 is going to be negative 3 over mu times du. And then the rest of this is just 1 over u. Haha. On the right-hand side, just t plus a constant. It's tricky. It's real tricky. Yeah. I don't know if there's any other way to do that other than seeing the trick. All right. So then we integrate this. We get -3 over mu times the natural log of the absolute value of u. But let's go ahead and plug back in what u is equal to, which is 1 minus mu m to the 1/3. So it's the natural log of the absolute value of 1 minus mu m to the 1/3 equal to t plus c. And now we're supposed to go ahead and solve for m. Who's writing these questions? Is this a book question or some terrible thing someone came up with? Okay. That tracks. All right, so solving for m here. Going to multiply both sides by negative mu over 3. So I'm going to get the natural log of the absolute value of 1 minus mu times m to the 1/3 equal to negative mu over 3 times t plus negative mu over 3 times c is still a constant. Let's call it C1. This is C naught. Law. I'm just disgusted by this. So then we e both sides. You get 1 minus mu times m to the 1/3 equals e to all this stuff. So it's e to the negative mu over 3 times t times e to the C1, which you know I'm going to call A. At some point, I guess we should plug in 0 and solve for A. I guess this might be a good moment. Sure, let's do it now. So we've got t equal to 0 and m equal to 1. Yeah, right. Okay. So then we have 1 minus mu equals A. Did 1 minus mu equals A. So then we can write that we have 1 minus mu times m to the 1/3 equals 1 minus mu times e to the negative mu over 3t. And then we can solve for m, which isn't too terrible. So we're going to have mu times m to the 1/3 is going to equal 1 minus all that. And finally, divide both sides by mu and take the third power both sides. So m should equal all of that divided by mu all to the third power. Wow. Yeah, that's fun. At least the next question is not that hard to answer. Remember that mu is positive, right? Yes. So then if t goes to infinity, e to the negative mu times t over 3 is going to go to e to the negative infinity, which goes to 0, right? If you think about the graph of e to the x, it goes to 0 as x goes to negative infinity. So you're going to get 1 minus mu times 0 all over mu cubed. So I think you should get 1 over mu cubed, or mu to the negative third. Yeesh. I don't love that. Okay, that's assuming we didn't do anything silly. I think that's right. It seems really awful though. Yeah.
When you move the 1 over, wouldn't it be -1?
So I did two things at once. I just didn't want to write it all down. What I really did was I moved the -1 over. So I had negative mu times m to the 1/3 equals -1 plus 1 minus mu times e to the negative mu over 3t. But then I multiply both sides by -1 to get the positive mu times m to the 1/3 equals positive 1 minus 1 minus mu times e to the negative mu over 3 times t. Yeah. Yeah, gross. Okay. Okay. Let's look at this next thing first. So we'll try to get to that. So we might not get to the 3D stuff and vectors till next week. But I have a handout that I think is worthwhile. Up and down. Right up and down. Up everybody. Thank you. Should be enough copies to make it to everybody. And I should not just abandon you here. Where'd you go? Okay. So, thank you. No. Sure. All right. So Euler's method, just to kind of make sure you really all know what's going on. I know we talked about it a little bit last time, but I really want to make sure that you guys are kind of clear with what's happening. So the whole idea here is, again, that if we're going to do, and we're going to do this graphically, and then we'll talk about kind of how you could not do it graphically. The whole point here is like, if I'm starting at y of 0 equals 2, I'm starting there. And the idea is that I'm going to take that point and I'm trying to estimate y of 2. So I want to know if I plug in 2 what my y value would be. So I'm going to take that point and I'm going to try and follow the curve. So if I just kind of followed it, I might guess something like about there. I don't know. But that's probably not right, at least not using Euler's method. So what I'm going to do, or what Euler's method tells us we should do, is we start at our point, and then we find the slope of that point, which looks like it's going exactly that way. And I'm going to follow that slope for this far in the x direction. So I'm going to go like that. It's good to use a straight edge here. So right about there. So if 0, 2 is my t naught, y naught, then it looks like 0.5, 1.5 is my t1, y1. So we started at 0, 2. We followed the slope of the direction field in that direction for a length of a half a unit. And then we found this new point, 0.5, 1.5. Then we're going to do the same thing again. We're going to start here, and then we're going to use the slope, which looks to be about whatever that slope is right there. We're going to follow that slope direction for another half a unit. Again, that's where the drawing is. So now it looks like our next point is going to be about, well, x is certainly, sorry, t is certainly 1. And the y value is about, I don't know, maybe 1.3. Yeah, let's say 1.3. That's my new y value. And again, all we've really done is taken our old y value and added to it, or subtracted from it in this case, the rise. Right? We're saying, okay, we know the slope is something. We could actually find the slope, whatever that value of that slope was, if we actually had the differential equation, and then multiply it by the run, which is 0.5, to figure out how much we're going to either go up or go down. Do it 2 more times. So from here, what does it look like my slope is? I don't really have, so it looks like it's maybe just it's kind of maybe in between all these things. So it's maybe just very slightly positive. So it might do something kind of like, I don't know, like that. And then from here, maybe slightly more positive, maybe like, I don't know. That seems let's see, less positive than that, right? More positive than that. Sure, okay. About that. So it looks like my next point was maybe 1.5, 1.35 is my t3, y3. And it looks like finally my last point is to be 2, about 1.5. So using this graph, I would approximate that y of 2 is approximately 1.5. So again, each t, y coordinate, we're using the slope of the direction field to point us in the direction to get to the next t, y coordinate. Just looking at what the Euler's method equation would give us if we did this one. So I'm going to make an assumption here that it looks like the slope right here at 0, 2 is about -1. It looks fairly reasonable, right? It looks like we're going over 1 and down 1 pretty much. So I'll point out that if my t naught, y naught is 0, 2, and if I wanted to find the next y value in the analytical way, well, my next y value would be y1 is going to be my old y value plus your run, your h, your step, times your slope, your differential equation, whatever it's equal to with the points plugged in, which you typically write as f of t naught comma y naught. In this particular example, my y naught is 2. My step size is 1/2. And again, like I said here, it looks like the slope of the differential equation there is -1. Right? If you plugged in f of 0 comma 2, you actually have the differential equation, it'd probably be, -1. And look, that's exactly going to give us the next y value of 2 minus 1/2, which is 1.5. So that's how the actual math of the formula works out, right? You're just taking your old y value and you're adding on how much you either went up or went down to get the new y value. And the way you're doing that is by taking how much run there is, how much you're increasing the x or the t by, and multiplying that by whatever the slope is at your starting point. Cool. We could also do the same thing. So then you could also do it here if you wanted to. This one's less exciting because your step size is bigger. So if you make your step size +1 instead of 1/2, I don't know why I said positive. Make your step size 1 instead of 1/2. Our first step would be to then go to like right there. So in this case, our t naught y naught is still 0, 2, but our t1 y1 is looking like 1, 1. And then from there, we would estimate the slope to be a little bit steeper than this, a little bit less steep than that. So maybe like that a little bit, and then we would go over 1 to end up about there. So a little bit lower. So I would guess here, my t2, y2 is about, I don't know, 1, 1.4. So I would guess that my y of 2 here is about 1.4. Okay, yeah, we got time. So let's look at the other side of this, because the other side of this actually has the differential equation that was used to generate this direction field. So this direction field is generated by the differential equation y prime equals 1/2 x minus 1/2 y. Let's write this over here for a second. So this is y prime equals 1/2 x minus 1/2 y. And notably, at the point 0, 2, if x equals 0, y equals 2, then my slope, y prime, is exactly 0 minus 1/2 times 2, which is -1. So yeah, it seemed totally reasonable to say the slope right there was -1. Cool, it works. The math here is going to get kind of gross, but it's worth doing. So we're going to do at least a couple steps of Euler's method here, the kind of the long, gross way. So we know that we're starting off with, and I guess I should have been using x's instead of y's. So our x naught comma y naught was the point 0, 2. And then to find my next y value, we already know it's going to be 1.5. We kind of did the math already. So our y1 is going to be our y naught plus our step size times the slope. And the slope is going to be, I'm going to call this here. Can you see that? No, you can't. Sorry. Apologies. You guys can see stuff. No. I'm going to call this f of x comma y. It's going to be f of 0, 2. I know I've said it like 3 times already, but I'm just going to say it again. My old y value, my run or my step size, my slope. The whole thing every time. So I'm going to get 2 plus 0.5 times f of 0, 2 is going to be -1. So that's going to be 1.5. And then we just do it again. So then our next y value is going to be the old y value plus the run times f of the new slope, which we get by plugging in our new x, or the next x value and the next y value. So, right, I should have written here that our x1 comma y1 was 0.5 comma 1.5. So then Here we're going to have f of 0.5 comma 1.5. And we're going to get, let's see, 1.5 plus 0.5 times f of 0.5 comma 1.5 is going to be a half of a half minus a half of 3 halves. So 1/4 minus 3/4, which is negative 1/2, times a half is negative 1/4, plus 1.5 is 1.25. So we were pretty good with our guess, right? Our guess was 1.3 at this stage. 1.25 is a little bit lower than that, but not unreasonable, right? Using a graph to get that. And then we could continue on. I don't think I need to continue on. But if you kept doing this, I'll just point out that the next one would be your old y value plus your step size 0.5 times f of your new x is 1, your new y is 1.25. And then if you plug that in, I'll just tell you it's going to be equal to 19/16. And then finally, if we do this one last time, our y4 is going to be our previous y value plus 0.5 times f of 1.5 comma 19/16. If you do that, you get, and also, well, I'll post the solution to this as well because you can see the math. This is going to be equal to 25/16, which is what, 1 and 9/16, which is just a little bit bigger than 1.5, which is pretty close to our guess of 1.5. So the graphical method really did get us to the graphical method is just doing the math, but not writing down all the numbers. And then we might as well solve the differential equation while we're here. I mean, why not? We've come this far. So let's solve this differential equation. So this is definitely a first order linear differential equation. So we're going to rewrite it as y prime plus 1/2 y equal to 1/2 x. We're going to find the integrating factor. Mu of x is going to be e to the integral of 1/2 dt, which is just, dx. So used to using t for these, but this one we're using x. So it's going to be e to the 1/2 x. So on the left-hand side here, we're going to multiply everything by e to the 1/2 x and get e to the 1/2 x times y prime plus e to the 1/2 x times 1/2 times y equal to e to the 1/2 x times 1/2 x. This becomes the derivative of y times e to the 1/2 x, still equal to this stuff over here. We integrate both sides. Oh, sorry, don't forget the derivative symbol there. That's important. So then y times e to the 1/2 x is equal to the integral of 1/2 x e to the 1/2 x. You would use integration by parts there and get, what would you get here? Interesting. You would get x e to the 1/2 x minus 2 e to the 1/2 x plus c. And then you would divide both sides by e to the 1/2 x to get y equal to x minus 2 plus c over e to the 1/2 x. And then if we look at the place we started, right, our initial condition was y of 0 equals 2, right? That's where we started on the graph, right, at 0, 2. Then we can solve for c and say, okay, great. If x is 0, we get 2 equal to 0 minus 2 plus c over e to the 1/2 x, 1/2 times 0. Well, that's just c over 1, so it looks like c is equal to 4. So then if we have y equal to x minus 2 plus 4 over e to the 1/2 x. If you plug in 2 for that, sorry, that's getting very messy. If you plug in 2 there, you're going to get 4 over e to the x, 4 over e, because you get 2 minus 2 plus 4 over e to the 1/2 times 2, which is approximately 1.47. So pretty good. And then if I had been really smart, I would have graphed it on the thing, but I didn't graph the whole thing. But you could totally, so it'd be kind of neat, like if you actually graph, I mean, if we could totally just graph it right now. So just so you can all see. If we actually graph this thing, y equal to x minus 2 plus 4 divided by e to the 1/2 x. If you look at this graph here and compare it to the what's going on here, oh yeah, it kind of looks like our graph would have that same sort of shape. So it seems reasonable that this is the direction field for that graph and that this kind of thing we have charted out here is a decent approximation of what the graph of the particular solution is actually doing. So hopefully I've said enough words about Euler's method that it makes some amount of sense what you're trying to do with it. Let's go ahead and look at the problem that's on the board though. And yeah, I think we'll have to wait until next week to talk about vectors and 3D graphing stuff. Yeah, because at some point we're definitely going to get to talking about doing some things with 2x2 matrices. Okay. So we're starting off with the differential equation. Let's move that arrow out of the way. It's terrible. Okay. We have dn dt equal to 0.5 minus 0.02 times n times n. Where n of t is the population size in millions of individuals per milliliter. Maybe we're talking about like cells or something. I don't know. Okay. So n is millions of individuals, whatever we're talking about. Probably not people if it's per milliliter. T is in hours. Sketch the direction field of the differential equation for values of n between 0 and 250. No. Yeah, drawing the direction field is the worst thing ever. I don't like doing it. Interesting though. Huh. So I'll point out that this differential equation is autonomous, right? There aren't any t's in my differential equation. So maybe this isn't quite as bad as most other times. Let's take a look. The question relates to graph the sketch. Okay, I guess it is. So when you're graphing the direction field, it's not like your phase plot where it's n and n prime. It's your dependent variable versus your independent variable. So let's 250. Okay. Why 250? I'm imagining do I have the right number of decimals? 0. I missed a decimal there, sorry. 0.002. I might start before I do any of this by thinking about finding your equilibria. So in other words, I'm going to think about where dn dt is equal to 0. Certainly, one of the things that makes it 0 is going to be n equal to 0. So along the horizontal axis, where n is always 0, the slope of the tangent line is also always 0. So it's kind of annoying to have to try and draw it. But in here, like you have all these little marks that are little horizontal direction lines. There they are. You see them? There they are. But also, more interestingly, if we solve this part equal to 0, the 0.5 minus 0.002 times n equal to 0. Let's use fractions. 1/2 minus 2 over 1,000 times n is equal to 0. So 1/2 equals 1 over 500 times n. So not surprisingly, n equals 250. Not surprisingly, because that's the value they give, right? 250, yeah, 250. So we go all the way up to 250 here. We're also going to get not a horizontal asymptote like I'm kind of drawing it, but direction lines that are all horizontal, because the slope there, no matter what your t value is, right? Again, this is autonomous, meaning if you look at one vertical slice, it should look the same there if you move left or right, because changing t shouldn't change anything about the differential equation. So once we figure out what's kind of going on this one little slice, we can just like repeat it left and right as much as we want. So let's see what's happening here. So if n is a little bit positive, bigger than 0, well, this part's always going to be positive, and this part's also going to be positive. So it looks like my slope is going to be, I guess I should plug in a value. This is the most, to me, sorry, I apologize for my disdain of this particular thing. It feels so tedious to have to draw these things, but let's do it. So let's pick a few values for n. So if n is equal to, I don't know, let's say 100, let's say 50. Yeah, we can break this up into like a 50, 100, 150, and a 200. Let's try that. If n is 50, then our dn dt is going to be 0.5 minus 0.002 times 50 is going to be 0.1, I believe, right? Because, yeah, minus 0.1 times 50, which is going to be 0.4 times 50, which is 4 times 5, which is 20. That's a pretty steep slope, right? A slope of 20. I'm not good at seeing that visually. It looks practically vertical to me. So, okay, here we have a slope of very steep. Hopefully it gets less steep if I plug in 100. I don't think it's going to get less steep. I think it's going to get more steep, actually. Right? I know, it's kind of silly. If you plug, so, right, if n equals 50, I get a slope of 20. If n is 100, so I'm going to have 0.5 minus 0.2 times 100, which is going to be 30, even steeper. Hopefully it's going to change directions here in a second. By plugging in, it should, because I eventually have to kind of flatten back out to 0. So if n is 150, I get 0.5 minus 0.3 times 150, which is 0.2 times 150, which is 30 also. Okay, so it stays like the same. I wouldn't be surprised if at 200 I got something more like 20. So I get 0.5 minus 0.4 times 200 is exactly 20. I suppose these are kind of wonky looking because of my scale, right? I should have made, like, these might look a little flatter if I adjusted for the fact that my n values are much larger than my t values, I'm thinking. So yeah, I got time. Sure. And then 20. And then 250 at 0. Yeah. But let's go ahead and look at this for a second. Where's the one I like? Not that. I think that's the one. Sure. Yeah, we can. Let's look at this. So I want this to be, I'm thinking of my y as my n and my x as my t. So I want dy dx to equal 0.5 minus 0.002 y times y. And then can I change my, there's usually a way, oh yeah, okay. So if I go from, like, it shouldn't really matter what my x type is, but -1 to 10. My y is going to go from 0 to 250. Interesting. Yeah, I mean, that seems, so the thing I said was happening is happening, right? No matter which vertical slice you take, you're getting the same thing from left to right. And then theirs looks nicer. Obviously, it's a computer. But right, so we're getting kind of some slopes here. So like here, the slope is 20, but it looks better because of the scaling, right? There's a lot more vertical scaling versus how much horizontal scaling there is here. So here we have a slope of 20, slope of 30, slope of 30, slope of 20, slope of 0. So there's our direction field. Interesting. And then they ask a question. If n of 0 equals 0.2, then Euler's method, good God. But they say use Euler's method, not so. Yeah, I don't see the point in doing. That's not true. I see the point in doing the graph. The question said to do the graph. That's the point of doing the graph. The question asks us to do it. As far as Euler's method here, usual stuff. So if I'm going to apply Euler's method, I'm going to do the usual thing. I have that my n of 0 equals 0.2. Or in other words, yes, thank you, good call. So that my t naught comma n naught is 0 comma 0.2. My step size is 0.5. I'm trying to get to, problem doesn't say actually what I'm trying to get to. 4 hours later, oh my gosh, I have to do this 8 times. Gross. So, right, so how do I have to do 8 times? Because my step size is half an hour. I'm trying to find out what n of 4 is, so I have to do this 8 times to get to 4 hours. Let's just do the first one and then we'll call it a day. So if I was going to find the next one here, my n1 when t equals 1/2 is going to be, well, it's going to be my old n value plus my step size times my f of 0 comma 0.2. And again, I know I've said it like a bunch of times already, but I'm just going to say this again. My old y value, this is my run, this is my slope. So in this case, it's going to be my old y value, which was 0.2 plus 0.5 times my slope, which I'm just going to get by plugging in this point to my dn dt here. Which is really kind of gross. 0.2? Yeah, I guess so. It seems, that feels wrong. NFT is the population size of a million. Okay, but the problem I have here is it's going to be very kind of small. So we're going to get times 0.5 minus 0.002 times 0.2 all times 0.2. That seems kind of awful. I feel like, yeah, I don't know. I feel like that wasn't the intended initial value, but maybe it really was. So then you would find your n1 and then do this 7 more times. Or ask your teacher if they meant for it to be slightly different. Because I feel like this is just going to be really, really gross. One thing I'll say that could make your life easier to do this is if you went over to Desmos or some graphing utility, if you went back to Desmos here, sorry, where'd you go? There you are. And you said, okay, I'm going to put in my differential equation. So essentially I'm going to say y equals 0.5. And yes, you're free to go if you need to go. Minus 0.002 x times x. So then I can just grab a table here and say, okay, well, I know that if x is 0.2, then there's my y value or my derivative value of 0.099992. And then you can take that one and do the next one. So then you can find your next value and put it right there. And at least it'll be slightly less terrible than having to throw all this junk into a calculator. It's not the best though. Yeah, it's not. Okay, that's all I got.